Hi everyone. We're going to start today on chapter 8, which is really just extending chapter 7. We're just utilizing potential energy, kinetic energy, internal energy in different applications. And we're also going to combine all those types of energy when we're talking about the conservation of energy. So, as a review, let's talk about the three methods for storing energy. So there's kinetic energy, there's potential energy, and then there's also internal energy. Those were the three types that we talked about in chapter 7. We know that kinetic energy is just associated with movement of members of a system. We know that potential energy is determined by the configuration of the system. And we talked about two types last chapter. We talked about gravitational potential energy, which is dependent on height. And then we talked about the elastic potential energy, which had to do with that spring force. The third type of energy was internal energy, and that was related to temperature. So usually if we have some type of internal energy, we see that that's related to heat and temperature somehow. Okay, so we also can think about, in terms of our system, there's two major types. There's non-isolated systems, and then there's an isolated system. In a non-isolated system, that's where energy can cross the system boundary in different ways. In a non-isolated system, then, ultimately what will happen, the total energy of the system is going to change. So in a non-isolated system, we can have energy that's passing through the system boundary, and it can happen in several different ways. It could happen through electrical transmission, it could happen through heat, it could happen through mechanical waves, it could happen through electromagnetic radiation. So there are a lot of different energy paths that can change that total energy for that system. The second type of system is called an isolated system. And an isolated system is where energy is not going to cross the boundary of the system, and the total energy of the system is going to remain constant. So usually I think about an isolated system where there's not really any interactions, or we kind of neglect then interactions between the environment and the system. So in that case, we think about the system as being isolated. There's nothing that's going to change that total energy for that system. I may just think about the kinetic energy and the potential energy that the system has, but nothing else is going to influence that. So these systems lead us to our conservation of energy. And the conservation of energy is just where the total amount of energy in a system is going to remain constant as long as we have this isolated system. Okay, so if we're looking at some examples of ways to transfer energy, we know that in a non-isolated system, energy crosses the boundary of the system, and that happens usually during some time interval because of an interaction with the environment. Now, the work kinetic energy theorem is the first equation that we usually go to when we think of a non-isolated system. Let's talk about some different examples then of ways that we can transfer energy. So work would be that first one, because a lot of times, like I said, we go and think about work kinetic energy theorem is an easy example of transfer of energy. So if I'm looking at this one, I see that energy is transferred to the block by work. So we can apply some energy based on interaction with the environment. We could also transfer energy through mechanical waves. And what that's doing is we're transferring energy by allowing some type of disturbance to propagate through a medium. So medium just meaning like water or air. And a sound of an alarm clock would be an example here. We could also have energy transferred in terms of heat. So we can have the mechanism of energy transfer, usually that's driven by temperature difference between two regions in space, is what we will call a transfer of heat. And I can see that just based on the internal energy of the spoon handle. So if I'm thinking about this spoon in my cup of coffee, ultimately the spoon handle is going to increase in amounts of its internal energy because it's in this cup of coffee. Another type of energy transfer would just be matter transfer, and matter is physically crossing the boundary of the system, and that's carrying energy with it. So we are, energy's entering, for example, a gas tank through matter transfer. So I'm pumping gas in my car, we're giving it energy. Another example would be electrical transmission. So that's just energy transfer either into or out of a system through electric current. So a hairdryer would be an example of that. Another example would be electromagnetic radiation. So it can just be transferred through electromagnetic waves. So that could be through radio waves, could be through microwaves, UV, gamma, visible, any of those types of electromagnetic radiation on that electromagnetic spectrum would be a good example. So energy leaving a light bulb is a good example. So this leads us to the conservation of energy, and ultimately we're just saying that energy is conserved. So it means that energy cannot be created nor destroyed. Ultimately, if the total amount of energy in a system will change, it can only be due to the fact that we have some type of transfer of energy. So that means that we have some energy that's crossed the boundary of the system. So it's either leaving the system, or we have the environment acting on the system, and we have energy entering into the system. So we have some type of energy transfer if the total amount of energy is changed. This has been tested thousands upon thousands of times through numerous experiments, and no one has been able to prove this to be incorrect yet. So we believe that energy will be conserved. So we can describe the conservation of energy in terms of a mathematical equation, and that would be as delta E, so just the change in energy, and let's be more specific, of the system is equal to the sum of all of the transferred energy. So we can, again, mathematically show the conservation of energy by saying delta E system is equal to sigma T. So that delta E for the system is just representing the change of energy in the system, or of that system, is equal to the energy transferred across the system boundary by some mechanism. So remember that the energy of the system is going to include all methods of stored energy. So I could think about the energy of a system in terms of potential energy, of internal energy, or the kinetic energy of a system may change. So when we're talking about delta E for the system, we're talking about three particular types: kinetic energy, potential energy, and internal energy. When we're talking about the sum of all of the transferred energy, then we can think about it through a couple different ways, and we have different symbols that we've established to represent transfer of energy. So for transfer of work, we can call that T work, but we also have been talking about work before as just the symbol W. So we've just been looking at a capital W when we say work. When we talk about heat, you probably know this back from chemistry when you were doing thermodynamics, and you were trying to find energy. You've used a lot of like Q equals MCAT. So we represent heat sometimes as Q. So when I'm talking about the transfer due to heat, then we're just going to symbolize that as Q. In other terms of transfers of energy, like mechanical waves, like matter transfer, then we're going to use these down here. So I'll use T. This should be a subscript MW. So T, MW is just transfer by mechanical waves. MT is just matter transfer. If we use TET, that's just going to be electrical transmission. And then the ER is just transfer by electromagnetic radiation. So if we really want to think about what's happening in a non-isolated system where we can have a transfer of energy, then you want to use more of this type of formula, because this is just going to be the expanded version of our delta E system equals that sigma T. So I could have the change in kinetic energy plus the change in potential energy plus that change in internal energy. All of that can be equaled to the different amounts of transfer of energy that we can have. So that could be equal to the amount of work that we've done, plus the amount of heat that we may have added or lost, plus the transfer based on mechanical waves, or the transfer of energy based on matter transfer, or the amounts of energy based on electric transfer through electric current, or the amounts of energy based on electromagnetic radiation. So that is ultimately the same thing as what we just said. Delta E for the system, again, which represents kinetic, potential, and internal, is equal to all of the different types of energy transfer that we can have. So ultimately, this is just a visual diagram of what we just talked about. We can be changing the system. So the system is what's containing that kinetic, potential, or internal energy. And I can change that if we do some type of energy transfer through the system boundary. So if we do work, if we do heat, if we have some type of mechanical waves, if we have some type of matter transfer, electrical transmission, or electromagnetic radiation. So we're going to have a change in that total amount of energy. And that change in total amount of energy should be equal to the total amount of energy that's crossing through that boundary. And this is happening if we're talking about a non-isolated system. All right, guys, I'm going to stop here. We'll pick up on another video talking about isolated systems and then doing some examples with them. And then I'm also going to continue on with what we do in terms of frictional force. So what happens whenever we have friction that's in play now? Because a lot of times we're just assuming so far that it's a frictionless surface. So I'll probably post that video tomorrow. And again, on Monday, don't forget that I'm going to give you an extra day to work in class on your roller coasters. So you'll probably have 1.5, maybe a small video that we'll have that I want us to have watched at least probably by Tuesday or Wednesday, because Tuesday in class we'll test your roller coasters, and then we'll kind of talk about those couple questions that we had at the end of chapter 7, and then look at the bonus ones as well, and then we'll probably ask and go over some of the questions that you've had so far on chapter 8. Okay, I'm also going to post a schedule, kind of an updated schedule of what we'll be doing this week in class. If you have any questions, email me, let me know. If not, then have a really great weekend. Bye.